In this brief lecture, we talk about the variance and standard deviation. We start from the beginning by showing through a basic data set how we might develop these measures of dispersion. Now, you can look at formulas for the variance and standard deviation. You can plug in numbers and you can get a result, but that result is only meaningful if you have an idea of what these things actually are and you understand the logic of these formulas. All formulas are based on some conceptual insight that their innovators had in producing them. So we start off with this first column here. We have x sub I. This is a variable. Okay, if it wasn't a variable, we wouldn't have that I there, and that might suggest that it's a constant. Now in some books you'll just see x without the sub I, but it's nice to put that sub I because it indicates that there's different values of the variable and that it isn't a constant. Here's our small data set, very, very small. You can imagine that these are scores in a classroom of 5 people. Imagine it's a very small class and people have gotten grades of 60, 70, 75, 80, and 90. Well, the first question I'm going to ask about this data set is, imagine if you want to know how much dispersion there was overall in the data. So imagine you get your test back, maybe you got one of the higher grades here, 80, and you'd like to know that on average, how different are scores in the classroom? That's a perfectly reasonable question to ask. If everybody in the class got 80, well then there's no dispersion. The variability is equal to 0. And so, as we'll see, the standard deviation would be equal to 0. But if some people in the class got 40 and other people got 100 and you got 80, then it suggests there is quite a bit of dispersion. So that's what we want to do with the variance and standard deviations. We want to be able to develop formulas that actually measure this amount of variation and dispersion in the data set. Now, again, we're starting with intuitive examples here. You look at this data set and you ask yourself, well, how might I even approach this idea of measuring variability? Well, how would you do it in a classroom? You would get your test back and then you would probably look at the person next to you to see what they got. You would say, hey, I got 80. What did you get? And that person may say, well, I got 70. Well, that gives you an indication of how much dispersion there might be. You look at the person on the other side of you and they got maybe 100. So you're trying to account for that dispersion. So the first thing we want to do in developing this measure is let's take the sum of the variable. That's a really good starting point. So here's my summation sign. I'm summing x sub I, and it's equal to 375. That's 60 plus 70 plus 75 through 90. Next, I'm going to take the average, the arithmetic mean. 375 divided by 5. I'm dividing by 5 because there's 5 pieces of information that went into that sum. That's how we compute any arithmetic average. And that's equal to 75. Well, let's work on a first idea for measuring dispersion. How about we do this? How about we take the value, each value, and subtract the mean? That would tell us how much difference there are from each score away from the mean. So that's what we do in this column here is we take 60 minus 75, 70 minus 75, so that's x sub I minus the mean, and that gives us a new column of scores, and these are called deviation values, d sub I. So 60 minus 75 is equal to negative 15. 70 minus 75 is equal to negative 5, and so on. We have deviation values, and at first glance it may look like these deviation values are great because they tell you how much spread there is away from the mean. Notice that in each case we're subtracting the mean, so if we think of that arithmetic mean as that center of gravity in the distribution, then those deviation values should tell us how much dispersion there is around that central value of the mean. How can we summarize this information? How can we summarize these deviations? One idea might be to sum them up. Here I'm going to take the sum of all of these deviation values. Well, when I take the sum of all the deviation values, what do I get? 0. Now, is that only true for this particular data set? No, it isn't. No matter what data set you have, any theoretical data set of numbers, if you take the sum of deviations around the mean, it'll always sum to 0. And when you consider this, this makes sense because the arithmetic mean is that center of gravity for the distribution. So by the very nature of how the arithmetic mean is defined, this has to hold true. So the sum of deviations equals 0. Now I want to point something out. Let's go back to this first column here. Imagine that this score was 60. Well, it is 60. Imagine this score was 61. This score, instead of being 75, was 62. This score was 63 and then 64. In that case, we would not have very much variability in the data, right? Not nearly as much as we have in this particular data set. 60, 61, 62, 63, 64, very, very little dispersion. Well, if I calculated those deviation values and then summed them up, what would I get? I would get 0 again. Like I said, any data set you have, the sum of deviations is going to equal 0. So I ask you this question. Is the sum of deviations around the mean a good measure of variation? Is it a good measure of variability? And the answer is no. Why? Because it keeps giving you the same thing. It keeps giving you the same thing. It's kind of like if I told you I'm going to measure a table and that measure is, say, 3 feet. And then I told you I'm going to measure the CN Tower. And I said that measures 3 feet. You'd probably say, wow, whatever system of measurement you're using is really, really poor. Because everybody knows the CN Tower is much longer than 3 feet. So if I measure something and it consistently gives me the same thing for everything that I'm measuring, it's not a very good measure. And so it is with the sum of deviations. This is a very poor measure of variability because it always gives you a constant. If I take the average of those deviations, 0 divided by 5 is equal to 0. So no better, this is always going to be true. So that's not going to work in expressing variability. Let's move on to the next column. How could we deal with this problem that the sum of deviations equals 0? Well, how about we remove the negative signs? That might be an idea because you can see why those sum of deviations are equaling to 0. It's because you have the negative values here and then you have the positive values here. And these are balancing out and producing that sum. So how about I take the absolute value of the deviations? Remember, when I take the absolute value means you're going to remove the sign. You're going to ignore the sign and just focus on the magnitude of the number. So the absolute value of negative 15 is 15. I've simply removed the negative sign. The absolute value of negative 5 is 5. What's the absolute value of 0? It's 0. Absolute value of 5 is 5, and so on. So I've taken the absolute value of the deviations, and now I'm going to sum those absolute values. This sum right here is equal to 40. And then when I take the average of those absolute values, I get 40 over 5 is equal to 8. This absolute value, sometimes we call it the mean absolute value deviation, or MAD. This is a perfectly legitimate measure of variation in certain contexts. This works very well in certain contexts in statistics and research, but it is not the measure of variation that we're going to end up adopting for our everyday computations of variability. This, for us, is just kind of a bridge to get us to the next spot. It's kind of just, this was just a suggestion on how to get rid of the negatives, but it's not the way we're going to proceed for both historical and technical reasons. Let's go over to our last column where we're actually going to develop the true measure we want. What's another way of getting rid of those negative values? I took the absolute deviation. How about if I squared those deviation values? If I square this negative 15 right here, what am I going to get? I'm going to get negative 15 multiplied by negative 15, and that's equal to 225. Notice something, that when you take the negative number and multiply it by a negative number, you get a positive number. That's getting rid of our negative deviation values. I'm going to do the same thing to negative 5. Negative 5 times negative 5 is equal to 25. If I move down here, the 0 is going to remain the same. If I go down here, 5 times 5 is equal to 25. 15 times 15 is equal to 225. So if you look at this new column of deviations, squared deviations, notice that we've successfully removed those negative signs by squaring the number. Again, by squaring the number, you get rid of the negative signs, and therefore, what condition have we avoided? We've avoided that sum of deviations equaling 0. Now we have the sum of squared deviations, and that, in this case, is equal to 500. 225 plus 25 plus 0 plus 25 plus 225 is equal to 500. The sum of squared deviations. Well, as before, as for the absolute value and just the sum of deviations, I'm going to take the mean. So the mean of the squared deviations is equal to 500 divided by 5, and that's equal to 100. This number that I've just calculated right here has a very special name, and it's called the sample variance. So we've arrived at a way of computing variability that doesn't always give us 0. It doesn't use absolute values, but rather sums the squared deviations around the mean, and it gives us 100 for this data set, and it's called the variance. So let's formally define the variance. To define the sample variance, we use big S squared. Now in some books it may be different. You have to always check the notation of your textbook to see how they're symbolizing the variance. But here I'm symbolizing as big S squared. Big S squared is equal to the sum of, these are deviations, so the sum of squared deviations. That's the same thing as I had up here. Squared deviations, these are the squared deviations. That's why I'm just writing it in compact notation here. The reason why I'm writing it out like this is so that when you see textbooks write it like this, you'll know what they're talking about. These two things are the same though. Divided by n, so the sum of squared deviations divided by n. The average sum of squared deviation is equal to 100. Okay, we've defined the variance. Now let's get to the last part of what we're going to talk about today, and that's the standard deviation. The variance is a perfectly legitimate measure of dispersion, and it's used all over statistics and research. However, if it had one drawback, you could say what? You can say that it's in squared units. Remember, to get the variance, what did we have to do? We had to square those deviations. So when I report this number of 100, it's still in squared units. A lot of times we don't want to deal with squared units. We want to deal with the original units that we set out with in our research. So I don't want to know what the squared deviation is for these test scores. I want to know what that average deviation is, not squared. I do not want it squared. So how do you unsquare a number? Let's go down here again. How do you unsquare the number? You take the square root of it. So the square root of that sample variance is equal to S, because the square root gets rid of the square, and that's equal to, there's the square root sign, and all I'm doing is taking the square root of this whole thing right up here. Okay, notice what we're doing. We're just taking the square root of that, that's all. When I take the square root of 100, I get 10 for our data. So when I take the square root of the variance, I get the standard deviation. The square root of the variance is equal to the standard deviation. If this number were, instead of 100, let's say it was equal to 9 for some data set. So the variance is equal to 9. What is the standard deviation? It's equal to 3. We can go the other way as well. If I take the standard deviation to be equal to 4, and I want to know what the variance is, just square it. 4 times 4 is equal to 16. That would be my variance. So one is always the square of the other. So the two things we've defined here are the sample variance and the sample standard deviation. Usually we use the sample standard deviation because of the fact that it is in unsquared original units. How can I use the sample standard deviation? Well, let's go back to the test example, the first column up here. You get your test back, you got the 80. Now, instead of comparing your score to everybody else's score in the class to find out, how much variability there is, it'd be nice if your professor told you that the sample standard deviation is equal to 10. What would that tell you? That would tell you that on average, people deviate from the mean by 10 points. See, it's an average. Just like the mean is an average, if I look here, this mean, this is an average. Well, so is the sample standard deviation. Only I'm averaging squared deviations. And it is a very, very useful measure of dispersion. If the sample standard deviation were large, then it would indicate that there is quite a bit of variability in your data. So imagine for this data, maybe the numbers would be different, and I told you that the standard deviation is equal to 50. Well, that means there's a lot more dispersion than if the sample standard deviation were equal to 10. And as that sample standard deviation gets lower and lower, that suggests that there's lesser and lesser variability. So if all of these scores were 60, for instance, if all of these scores were 60, what would the sample standard deviation be? Well, you don't need to do the computation. You just need to ask yourself, well, if all the scores are 60, that means there's no variability. Therefore, I guarantee you the sample standard deviation would be equal to 0, as would the variance. So the two measures of variation commonly used in statistics and research are the sample standard deviation and the variance. There's one thing I want to point out to conclude. Notice that the denominator of the sample variance and the sample standard deviation is equal to n, okay, because we've said it was the average squared deviation. In some cases, this will not be equal to n. This will be equal to n minus 1. Now, the reason why, so you'll have sum of square deviations divided by n minus 1 here. Same thing down here. There will be an n minus 1 instead of just n. The reason for that is beyond what I want to talk about today, and it has to do with degrees of freedom. But I want you to know that when you see this in textbooks, when you see the n minus 1 in that denominator, it doesn't really change the whole meaning of what the sample variance and standard deviations are. They are still the same thing. We're just using a slightly different denominator when we compute the measure of variation. So don't think it's something entirely different. And in a later discussion, the topic of degrees of freedom will come up, and that'll explain why we're subtracting the n minus 1 in the denominator. So I hope this brief tutorial was helpful in helping you understand the variance and standard deviation.